Okay, this topic is on non-parametric statistics, and we are looking at those kind of tests which we use when the assumptions for parametric statistics have failed to hold. We are also going to look also at goodness of fit tests. Under goodness of fit test, in this test, the experimenter has reason to believe that the response variable follows some particular family of PDFs, probability distribution functions. That's what we mean by PDFs. But there is little or no prior information to suggest what values should be assigned to the model's parameters, right? In cases such as these, we'll carry out the goodness of fit test by, of course, first estimating all unknown parameters and then computing the required chi-squared test statistic. And by parameters here, for example, if you are dealing with the Poisson distribution, it is only one parameter, which is lambda, which serves as both the mean and the variance of a random variable, of a Poisson random variable. And the chi-square test statistic is given here, the sum of OI right here. This is OI, which is the observed minus the expected frequencies, the EIs, O squared over the expected frequency. The distribution is chi-squared with K minus R minus 1. Here K refers to the number of classes under consideration, and R is referring to the number of parameters estimated. In the example of a Poisson distribution with R equal to 1, where R is simply equal to the number of parameters, which is lambda. That is the only parameter that we estimate under the Poisson. But if it is given already and doesn't have to be estimated from the dataset, then it means we are not estimating any parameters and R will be equal to 0. For a normal distribution with mu and sigma squared as the only two parameters, it means R will be equal to 2 if both of these parameters have to be estimated from the dataset. Otherwise, if they are given and we don't have to estimate them from the dataset, then again we'll say R is equal to 0. So let's discuss this through an example. In the first example, in this case, we are considering coronary artery bypass graft, CABG, surgery, and patients are encouraged to participate in a cardiac rehabilitation program. The program lasts about 14 weeks and includes exercise training, nutritional information, and general lifestyle guidelines. So one hospital is offering 3 cardiac rehab programs that are identical in content, but are offered at 3 different times. Each patient is asked to select one day and time that is convenient. So you are like selecting Mondays, Thursdays, or Saturdays at those given time slots. The day and time variable is approximately multinomial with K equal to 3. That is, we have 3 classes there, Mondays, Thursdays, and Saturdays. The proportions of patients in the sample selecting each day and time are given by PI, where equal to the number of successes over N. We calculate N to be the total number of observations here. We have 47 in the first class, 32 in the second, and 21 for Mondays to give us 100. So we have to test the hypothesis that the 3 day and time options are equally popular, meaning we are saying the proportion of people choosing Monday and those choosing Thursdays and those choosing Saturdays are actually the same. That is what we want to test here. In this kind of goodness of fit test, we are not estimating any parameters. We already have the proportions here, because P will be equal to 1/3 in this case, because we say all the 3 are equally likely. So we say 1 over the 3 categories which we have here. The solution, The null hypothesis says the three proportions are the same versus proportions are not all equal. We are testing at 5%. The appropriate test statistic is obviously the chi-square with 3 classes in this case, and R is equal to 0 because we are not estimating any unknown parameters here. Okay, so the test statistic is as given, and the issue is on how to get the expected frequencies. We use EI is equal to NPI, where N is the total number of observations, which is 100 in this case, and PI is the appropriate proportion for each of the classes. So this is what we are going to do. Our decision rule in general will reject H0 if chi-squared is greater or equal to the critical value, which is chi-squared k minus 1 at a level of significance alpha. We now have the revised table there with the quantities. Expected value of 33.3 there, given in the first class for Mondays, is found by multiplying 100, this 33 here, this one, we get this by multiplying 100 by 1/3 because the proportion for those coming on Mondays is 1/3, which is the same as those coming on Thursdays as well as those coming on Saturdays. This is why you see we have 33.3 and 33.3 in all the 3 classes. It's because we had the same proportion of 1/3 as for all the classes. Now, you then have to use the observed minus EI squared over EI. To get 5.64 here, it means we subtracted 47 minus 33.3. We squared that difference and then divided by 33.3 to get 5.64. The same applies to this class here. It was 32 minus 33.3. You square the difference and then divide by 33.3. Overall, if you add 5.64, 0.05, and 4.54, the test statistic becomes 10.23. We then go to our chi-square distribution tables, where we say, we had k is equal to 3. So the number of degrees of freedom is k minus 1, which means we now have 2 degrees of freedom there to give you a critical value of 5.99. Therefore, based on the value of the test statistic of 10.23, we are rejecting the null hypothesis in this case, which means we have significant evidence at the 5% level, and that's the level at which we tested, that the 3 time slots are not equally popular or convenient for the patients. Let's go to the second example. In this case, you have volunteers at a teen hotline who have been assigned based on the assumption that 40% of all calls are drug-related and 25% are sex-related, 25% are stress-related, and 10% concern educational issues. This investigation, each call is classified into one category based on the primary issue raised by the caller. So you have that data set here. Drugs with the number of observed is 52. The number of calls there for sex is 38, stress is 21, and education is 9. Based on the data, is the assumption regarding the distribution appropriate? So in this case, we are given the proportions as 0.40 for 40%, 0.25 for P2, which is for the second category, which is also the same for the stress category. Then we have 0.10 or 10% for the education category. So our null hypothesis would indicate that P1 is 0.40, P2 is 0.25, is equal to 0.25 again for P3. Then we also have P4 is equal to 0.10. We calculate the expected frequencies as before. We Note that with 52 plus 38 plus 21 plus 9, that would amount to 120. So you are multiplying 120 by 0.4 to get the expected frequency for the first class. And then you multiply by a quarter to get for the second and third class, and then you find E4 is 10% of 120, which is 12. The solution here is as follows. If you sum the observed minus EI squared over EI, you'll get a 5.913 as your test statistics. I'm sure this slide was meant for the student to do and verify that they'll get the 5.913 there. We have 4 classes, and hence we have 3 degrees of freedom. So we have chi-squared 3 there as 7.82. As you can see, that 5.9 is smaller than 7.82. We fail to reject the null hypothesis and conclude that the distribution of topic issues in the course placed to the tree-note line is assumed. These 2 examples did not include a situation where you have to estimate n unknown parameters. The proportions of probabilities were already known. But you might find a situation where you have a given data set and you're supposed to fit a probability distribution function with an unknown parameter. So in this example, we have the number of computer malfunctions per day, which was recorded for 260 days with the following results. So xi there is simply the number of malfunctions, meaning that 0 and 77 would mean that there were 0 malfunctions for 77 days, which means each of the 77 days did not record a single malfunction. Then we had a single malfunction for 90 days, meaning that each and every one of the 90 days, there was just 1 malfunction there. We had to test for goodness of fit of an appropriate probability model. In this case, we have to find out from the different probability distribution factors that we know what this particular, what a suitable PDF should be. So looking at these accounts, so an appropriate model here could be a Poisson based on the following. One, we assume that malfunctions occur independently, and that simultaneous malfunctions are also impossible. Malfunctions occur randomly, and malfunctions occur uniformly. Mean number per time period is proportional to the length of the period, which these assumptions actually are the assumptions for the Poisson distribution. So we propose the use of the Poisson distribution here, which means we want to test the hypothesis that the data conforms to the Poisson distribution. So we have to estimate initially the only parameter, the mean or lambda of the Poisson. So with lambda hit, equal to sum of xi fi over n. In this case, we are saying the observed value there, we have xi 0 times 77, then we're adding to 1 times 90, then we're adding to 2 times 55, then we have 3 times 30, and 4 times 5, then 5 times 3. That would give you a sum of 325. We already know what n is with 260, but you can find this one by adding the observed frequencies from the previous slide. In short, you are adding 77 to 90 to 55 to 30 to 5 and to 3. You should be able to get the 260, which is the number of observations which we have. Since we don't know the proportions or probabilities, it means we have to calculate them from the Poisson distribution. So for x equal to 0, we simply have to find the probability of x equal to 0. And This is done by substituting 0 whenever there is x in the PDF. As you can see, we've indicated what lambda is. It's 1.25 here. And therefore, when x is 0, we are simply putting 0 where there is x there to get the various probabilities which you see. The expected frequencies are found, as we've done before, by saying n times pi. So for the first class, n is 260 multiplied by the probability of x equal to 0, which is 0.28650 to give us a 74.5. We do the same for the next class where x equal to 1. The probability is 0.35813. And then the corresponding expected frequency is NPI or NP1, which is 260 multiplied by 0.35813 to give us a 93.1. This is done for all the classes, as you can see here. We then take note of the fact that the expected frequencies should all be greater or equal to 5. So here you see 1.9 is smaller than 5 and 0.5 is also smaller than 5. We need to join these two classes together and check if the collective expected frequency is now greater than 5. If it is less, we then join to the class with an EI of 7.6, which is above them. Here we note that 0.5 and 1.9 gives you a 2.4, which is smaller than 5. So we have to join that class to the one with 7.6. That would mean that the expected frequency would then be greater than 5. It will be equal to 0.5 plus 1.9 plus 7.6. That is actually an expected frequency of 10. This is what we are talking about here. All expected frequencies should be at least 5. The revised table is as follows. Instead of going to 5 and above, we are now ending at greater or equal to 4 here. We had two classes below this, which had the 3 and the 5. So now the observed is 8 if you add 3 and 5. Then you can see that the expected has been changed to 10 or adjusted to 10. In the last column, this is where we are trying to calculate the test statistic observed in this first row here. You have 77, this 77 here, minus 74.5 squared divided by 74.5 to give you a 0.084. You do the same for all the classes and then calculate by summing 0.084, 0.103, 0.176, 1.39, and 0.4. You are summing to get a 2.153 there. That is your test statistic. The null hypothesis, this should normally come first. We are saying the number of malfunctions is distributed as Poisson, and the alternative one says the number of daily malfunctions is not distributed as Poisson. So we need to make a decision now whether to reject H0 or to fail to reject it. So we go on to find the critical values from the tables. In this case, we are using chi-squared k minus r minus 1, but our k is equal to the number of classes in the last class, which is this class here. This class is 5 classes. This table is 5 classes, this table is 5 classes. From 0 there up to greater or equal to 4, we have about, there are 5 classes. So if k is equal to 5 and r is equal to 1, because we've estimated lambda. So we now have k 5 minus 1 minus 1, which is 5 minus 2 to give us a 3. And a 7.82 from the chi-square distribution tables. Compared to 2.153, we actually reject the null hypothesis in this case. If we reject H0, of course, we conclude that the data does not conform to the Poisson distribution. which is basically our conclusion. So next slide is about the test for independency. We want in this case to test whether or not two categorical variables are independent. So our null hypothesis will indicate that the two variables are independent, while the alternative would indicate that they are associated or they are dependent. That is the interest of this slide. So we are testing if two variables are actually independent. So we would want to also go through an example. The following data were collected in a multi-site observational study of medical effectiveness of type 2 diabetes. So type 2 diabetic patients were enrolled in the study from each side and monitored over a 3-year observation period. So we have the site there, HMO, UTH, hyper, and then the exercises with diet and exercise, oral, hypoglycemics, and insulin. Those are the three types of exercise and size. So ideally, you are given only the observed values. Initially, 294 for the first row, first column, the 827 and 579. To give a total of 1,700. In the second row, you have all that, and we are adding the observed values in terms of rows as well as in terms of columns. So this is a 3x3 cross tabulation of contingence table. We want to test the hypothesis that site and treatment regimen are independent. So in the next slide, we want to test the hypothesis that site and treatment regimen are independent, or that site and treatment regimen are associated. This is always the kind of hypothesis you use if you are testing for independence. Then how do we get our expected cell frequencies? Because for you to use a chi-square, you would need to find the expected frequencies for each of the cells. In a 3x3, you have 9 cells, so you need about 9 EIs, or expected values. So you are going to say row total. In the first row there, you have 1,700 times the column total, which is actually 615, divided by the grand total here, which is 3581. This is the hypothesis. This is how we are going to calculate the expected frequencies. So, for instance, in the first row, second column, you have 1,700 here, multiplied by 1,631, divided by 3581. That would give you 774.3. Now let me pick the last cell there in the third row, third column. You are looking at 1109 multiplied by 1335 divided by 3581 to get a 413.4. That would be your expected frequency. We make a substitution into the chi-squared formula and sum as before. We'll get a chi-squared of 34.629 vis-a-vis a critical value of 9.50. One issue here is how do you calculate the degrees of freedom when you are dealing with a contingence table above. You would say the number of rows, which is 3, minus 1, times the number of columns, which is 3 again, minus 1. So with 3 minus 1 times 3 minus 1, which is the same as 2 times 2, which gives us a 4. And going to your chi-square distribution tables, you will get a critical value of 9.5 at the 5% level. So here it's obvious we'll have to reject the null hypothesis since 34.629 is greater than 9.50, and the conclusion follows through. Okay. Now we have come to the kind of test you would use when the one-way analysis of variance assumptions fail to hold, right? I think you would need a non-parametric procedure now to do that. If the assumptions for the one-way ANOVA fail to hold, you have no choice but to resort to a non-parametric procedure. So the Kruskal-Wallis test was developed to do exactly that. right? It assesses for significant differences on a continuous dependent variable by grouping independent variables with 3 or more groups. So we need 3 or more groups. In the ANOVA, we assume that the distribution of each group is normally distributed and there is approximately equal variance on the scores for each group. But of course, the Chi-squired do not have any of these assumptions. And one thing to note is that the Chi-squired is actually weaker or less powerful than the analysis of variance procedure. What is the hypothesis to be tested under the Chi-squired test? You are saying the samples are from identical populations, and the alternative is that the samples come from different populations. The assumptions for the Chi-squired will follow. We assume that the samples drawn from the population are random, and we also assume that the cases of each group are independent. The measurement scale should be at least ordinal. This is in order that we be able to rank the observations. We can only rank if the observations are at least ordinal. So the procedure, you arrange all the data in a single series in ascending order, which means irrespective of which group it came from. You assign them to ranks in ascending order, and if there is a tie, then you can actually find the mean of the ranks. Then you sum up the different ranks for each of the different groups, and you denote those ones by R1, R2, R3. In a nutshell, you actually replace the original data with ranks. Okay, you replace the original data with the corresponding ranks. And then for each of the different groups, you then sum those ranks. And those are the R's, which is R1 for group 1, R2 for group 2, R3 for group 3. In the end, you would need to substitute those values in the test statistic, which is H there, is given. N is simply the total number of observations we have. So if you have 3 observations in group 1, 5 observations in group 2, that means, and 4 observations in group 3. So you would add those together to get your N in that case. The rejection criteria, you reject H0, of course, if the test statistic H is greater than chi-squared k minus 1. Here, k is simply the number of groups involved in the analysis. Otherwise, we fail to reject H0. Let's look at this example. Group of depressed people is assessed for depression and found to be equally depressed. So you have each of them is then randomly allocated to one of 3 groups: no exercise, 20 minutes jogging, and 60 minutes jogging. So we have the data set as given here. This is the data. You have about 1, 2, 3, 4, 5, 6, 7, 8 observations in each of these categories. That is what we have. You are to test whether or not physical exercise alleviates depression. So the ratings are ordinal, hence Chi-squired is appropriate. So you have to pull all those observations together and rank them. So you arrange them in ascending order. I think the minimum observation here is 22, which is actually the first observation under jogging 20 there. And we have now we are going to replace the original data with the ranks. From here, it's quite clear that 23 is ranked 2 and 26 ranked 3 and 51 there is ranked 16. Then 49 is ranked 14, 58 has a rank of 19, 37 has a rank of 7, and 29 has a rank of 5.5, and so forth. You then sum to get R1, which is 76.5. Okay, you do the same in the sum to get 79.5 and 144 for the third class. So the idea is pull everything together, arrange them in ascending order, then assign ranks to observation. Replace original data with the ranks. And for each of the categories or groups, add or sum the ranks, and then you get the RIs, which is R1 for group 1, R2 for group 2 and R3 for group 3. Those are the values of 76.5, 79.5, and 144. These are the values we need in the Kruskal-Wallis test statistic. So N is equal to 24, which is simply the sum of all the observations. And we are showing you R1 there being the sum of all the ranks in group 1 there is 76.5. You can actually do the same for R2 and R3. We then calculate our test statistic H as follows: 12 over N, which is 24, and then times N plus 1, which is 25. This is R1 squared over the number of observations R1, which is 8. We do that up to the last group, add them together. We then subtract 3 times N plus 1, which is 24 plus 1 there. Please take note that 12 over 24 times 25 is only multiplying the sum of those values inside those brackets, right? And then we get here an H of 7.27. Finally, we'll be able to make our conclusions based on the decision here. Of course, chi-squared with the 2 degrees, that's 6, and 7.27 is actually greater than that, which means we reject the null hypothesis. And the conclusion is that there is a significant difference among the 3 groups. The last thing that we are going to consider is the rank sum test. An underlying assumption for appropriate use of the 2 independent samples test was that the continuous outcome was approximately normally distributed, or that the samples were sufficiently large. When we're dealing with independent samples t-test, we needed a very large sample, in that we assumed that the samples come from a normal population. Okay. Then when those assumptions are not holding, of course, we can then resort to Wilcoxon rank sum test. When comparing 2 independent samples, when the outcome is not normally distributed and the samples are small, we then use the Wilcoxon rank sum test. And this test is also called the Mann-Whitney test. The Mann-Whitney test, sometimes called the Wilcoxon rank sum test, is used to test whether the 2 samples are likely to derive from the same population. So here is the procedure. The null hypothesis that the 2 populations are equal versus they are not equal. You pull observations together again as before, and then assign them ranks. In this case, there are only 2, rank 1 and rank 2 there. Then N1 is the number of observations sample 1, and N2 the number of observations sample 2 or group 2. You then calculate the test statistic, which is U. U is a minimum of U1 and U2, where U1 is N1, N2, plus N1, N1 plus 1 over that minus R1. The same applies to U2 there. The critical values can be found using both N1 and N2 as well as the level of significance given. And you are using the Mann-Whitney U tables. That's what you have to use. In this particular case, you reject H0 if U is less than U critical. I think everyone can easily follow the example that follows there. N1 is 8, N2 is 8 there. Pull them together, all those observations, and then replace original observations with ranks, and then sum the ranks to get R1 is 42, R2 is 94. Make a substitution to U1. So there is also U2 is not U1 and U1 to get 58 and 6. U critical there is 30. So you would actually reject H0 in this case because the test is U is less than the critical value. Okay, that will be the Wilcoxon rank sum test for you.